Hello, welcome to this video. So we've done a lot of videos on this playlist, but after a lot of videos we finally got to the point where we can derive one of the most famous equations in physics, E equals mc squared. It's very rare in physics an equation becomes so famous that everyone seems to know it, but Einstein did it with E equals mc squared. So we'll be deriving it. But we'll be doing more than that. We'll be trying to really understand this equation. We'll be really trying to understand E equals mc squared. So when deriving it, we'll be using standard techniques in A-level maths. So I'll avoid things like, certain types of integrals called Lebesgue integrals. Because Lebesgue integrals are very useful when deriving equals mc squared. They allow a very elegant derivation, but Lebesgue integrals have hidden within them a concept which is very hard to physically interpret. So I try to avoid them like a plague, at least on playlists heavily focused on physics. Also, Lebesgue integrals aren't too commonly known, so to try to make an approachable derivation of E equals mc squared, we're going to use standard methods in A-level maths like integration by substitution. Also, we're going to try to really understand what E equals mc squared means, and it's worth doing that because the idea of associating energy with mass sounds slightly absurd, because we traditionally think about energy to do with motion. If we say something has a lot of energy, we think of it moving very quickly. So to then just talk about energy for an object that's completely stationary, in other words, energy just to do with an object's mass, seems really absurd. And so we'll also, after we've derived the equation, be understanding kind of why we should kind of expect, using ideas of relativity, that there should be energy associated with the mass of an object. We'll be looking at it kind of from a very physical perspective, and we'll also be using kind of slightly more mathematically technical details about four vectors and stuff, using ideas we have developed in this playlist. But if this is your first time coming to this video, this is hopefully a fairly standalone video, and will be, at least in terms of deriving E equals mc squared, and much of the explanation of what this equation means. Although we will have a few technicalities, but in terms of a technical understanding, in terms of the principles of relativity, of why equals mc squared, but there are plenty of videos on this playlist going into more depth on those technical details if you wish to look at them. But I thought this was a worthy addition to current content out there, because this is both an approachable discussion of E equals mc squared in terms of deriving it, and also trying to understand it, because unfortunately many textbooks derive it, sometimes in some very abstract ways, but very rarely do they take the time to try to understand what this equation E equals mc squared actually means. And we'll be seeing it comes out of essentially looking at how time dilation impacts our equation for kinetic energy. So we'll define kinetic energy, and we'll see when we use time dilation and we apply that relativistic principle to the definition for kinetic energy, we'll end up with a term in that equation for kinetic energy, which ends up being R equals mc squared. And so ultimately E equals mc squared is caused really by time dilation, as we'll look at in this video. If you haven't seen time dilation before, don't worry, I'll be summarising it when we get to it in this video as well. And then in the next video we'll look at applying equals mc squared to understand how the sun can produce such vast amounts of energy for such a large amount of time. We'll be applying equals mc squared to nuclear fusion processes in the sun, and we'll therefore be using it to get a kind of time scale for how long the sun can survive on its current stable main sequence space. So we'll be applying equals mc squared to astrophysics and to a wonderful sun in the next video, but this video will be about deriving it in a very approachable way and also understanding the equation we have derived. So, as we mentioned in our introduction, a natural type of energy to define is energy to do with motion. In other words, kinetic energy. You might think of other types of energy, for example, thermal energy. However, kind of like if we say an object is hot or has a lot of thermal energy, we're really talking about the sum of the average kinetic energy of the molecules in that substance. So we're still ultimately talking about kinetic energy. It's just kinetic energy associated with random motion, randomized motion, in other words, thermal energy. But often, in classical physics, all energies really boil down to either kinetic energy or the potential for kinetic energy. So a suitable place to start any description of energy is kinetic energy and defining that. And once we've defined that, we can look at what it is in classical physics, and we'll see, therefore, why in classical physics we wouldn't expect there to be energy associated with the mass of an object. But then we can also apply this definition to relativity using assumptions of relativity such as time dilation, which we've developed in this playlist. And this assumption will lead to a relativistic equation for kinetic energy, which will actually imply that there should be energy associated with the mass of an object. So we have to define generically what we mean by kinetic energy in the first place, before we can either look at the classical or relativistic kinetic energy. Well, we can think of the kinetic energy something gains as kind of like or something has, if you like, as the energy it's been given when it's been accelerated by a force from a velocity of 0 up to the velocity v, we're describing the kinetic energy at. In other words, kinetic energy is to do with applying a force on an object, and at least a change in kinetic energy is to do with applying a force in the object, therefore accelerating. So it's natural that force should come into our equation for kinetic energy, and also force times distance as units of energy. So if the force is constant, then we just define the change in kinetic energy, or in other words the work done on the object, to use more engineering language, to be just equal to the force acting on the object multiplied by the distance the object moves whilst that force acts on it. However, if the force is varying as the object is moving, then we have to integrate to take account of the varying force. So where the force is varying kind of explicitly or implicitly, we have to use this integral. And now we've got a definition for kinetic energy, we can then apply assumptions in classical physics to see what we get for kinetic energy in terms of velocity, and then we can also apply later our assumptions from relativity to get a relativistic equation for kinetic energy in terms of velocity. So if we're looking at the classical perspective, if you like, Newtonian perspective, because Newton's laws are all about motion, so really we mean the Newtonian perspective, we make a core assumption in Newtonian physics, which is very important for this video, because it heavily impacts the equation we end up with kinetic energy. And this assumption is that time moves at the same rate for observers. So, for example, if 1 hour passes for me, then um, you know, 1 hour will also pass for my cat Arwen. And it doesn't matter whether Arwen is sleeping on the sofa soundly, whether Arwen is naughtily jumping on the tabletops trying to, excavate dinner, um, or whether Arwen is, playing with pigeons. Time moves at the same rate for me and Arwen, and indeed, we assume in Newtonian physics, time moves at the same rate for everything in the entire universe. It doesn't matter where it is or what it is doing. There is some kind of universal passage of time. Now, on reflection, that assumption is actually incredibly dubious because we would almost need another universal principle to really explain why there should be a universal passage of time. Just postulating time moves at the same rate for everything in the universe, no matter where it is or what it is doing, is actually, on reflection, an incredibly um, general and strange statement to make, strange in the fact that it sounds like we would need a further principle to justify it. So, we really should be dubious of this assumption, and relativity, in fact, tells us that, yes, we should be very dubious about it. But in the context of classical physics, we make this assumption. This assumption works very well in daily life, at least to such a high degree of approximation, it's almost completely true, and for practical purposes can often be taken to be completely true. For example, like, say one of your friends has a birthday today, you can be quite confident that if you wait a year and then call them and say happy birthday, they won't respond going, what do you mean? It's only been 6 months since my last birthday. You can assume if a year has passed for you, a year will have passed for them. So we make this assumption actually that there's some universal passage of time all the time in daily life. It's a necessary kind of practical assumption for us to make. So if we make that assumption, we can then be very relaxed about the time interval we're talking about. Particularly, we can assume that time for the moving object moves at the same rate as time for us, the stationary observer, which is applying the force causing the object to accelerate. And therefore, when we define force to be the rate of change in momentum with respect to time, we don't have to worry about what time we're talking about, whether it's time as it appears to be for the moving object, or time as it appears to be for us as a stationary observer. And so force is just dp by dt, the rate of change in momentum. And if we substitute this into our definition for the kinetic energy, we end up with the kinetic energy in the classical case is the integral of the rate of change in momentum with respect to time integrated over the distance s the object has moved. Now we really want to play around with this because we want an expression for kinetic energy which will relate to the velocity of the moving object, because we said energy is to do with motion, so we really want to relate energy to velocity if at all possible. Well, at the moment it doesn't look like we have velocity anywhere in this equation for the classical kinetic energy, but we can be a bit sneaky. And it's sneaky because in reality dp by dt is a derivative and therefore is ultimately about limits and is not a traditional fraction, and we shouldn't manipulate it like it's a traditional fraction. However, because it's inside an integral, it turns out we can actually manipulate it as if it's a ordinary fraction. And that means we can replace dp by dt times ds with ds by dt times dp. And ds by dt is velocity, because ds by dt is the rate at which the position of the object is changing. And that allows us to bring velocity into our equation for kinetic energy. So if you do that, and you also bear in mind that the definition for momentum is mass times velocity, and also that as an object is accelerating, it's not changing its mass, so we can pull mass m outside our integral, we end up with the classical kinetic energy is a half mv squared, an equation you're probably very familiar with from GCSE physics. A very popular equation, you've probably seen it a lot. GCSE textbooks love it. when you're looking at an apple falling and seeing the velocity it hits the ground, you'll be making use of this equation for the kinetic energy. So it's a very standard equation. Now, for those of you that like to be a bit mathematically rigorous, you might think, oh, we haven't put a constant of integration into a formula for the kinetic energy. And because we haven't got any limits on the integral, we really should do this. Well, we haven't put a constant of integration here, because if you were going to add it, then you would find it would have to be 0, based on the fact that we define the kinetic energy of an object when it's stationary to be 0. So in other words, if V is 0, the kinetic energy has to be 0. And that implies that your constant of integration would have to be 0. So we can ignore the constant of integration. Now, if we look at our classical equation for kinetic energy, and this is important because we're going to compare this to the relativistic case. The classical equation for kinetic energy has a single term. That single term would be 0 if V would be 0. In other words, there's no energy term present in our equation for classical kinetic energy, which is energy which has nothing to do with motion. In other words, there's no equation with energy on it. There's no term in our equation for classical kinetic energy which indicates an object should have energy even when it's stationary, so even when V is 0. Now that's very different than the relativistic case, as we'll come on to seeing. But to get to the relativistic kinetic energy, we have to get to an expression for force F to plug into our definition for the kinetic energy. Now, defining force F was very straightforward in classical physics because we just said F is the rate of change of momentum with respect to time, and we didn't have to worry about what time we were talking about. However, this is not the case in relativity. In relativity, there's an effect called time dilation. Now, I'm going to go through it kind of a little here, particularly kind of like to make this video as accessible as possible for people who are starting the playlist from this video. And therefore might not have seen much about time dilation before. But if you'd like to learn more about time dilation, we'll talk about it in a fair amount of detail in the previous video where we apply it to effects like muon decay. But to summarise time dilation is ultimately the idea that if we were going to put a clock on a moving object, i.e. an object moving relative to us, and the velocity of the object was going to increase, we would see the clock tick slower and slower and slower. In other words, time, it appears to us, seems to be slowing down for the moving object the quicker the object moves. And we see this, for example, in muon decay. If a muon is travelling very quickly, it will take a lot longer to decay from our perspective than it would if the muon was just stationary relative to us. So this is the effect of time dilation. And because we're accelerating an object, the object that's gaining kinetic energy gains it through acceleration. Obviously, the object has some velocity relative to us, and that velocity once more is changing. And therefore, it's very important to distinguish between the time interval, in other words, the amount of time that has passed, for what appears to us to be the amount of time for the moving object, and the amount of time we would consider as having passed, if we were holding the clock and looking at the clock. If we say the amount of time that has passed for us, so if we look at the clock stationary relative to us, is dt, and the amount of time that has passed for the moving object, at least from our perspective, would be dt prime, then dt and dt prime are related to each other by the equation dt equals gamma dt prime, where gamma is a Lorentz vector. And as the velocity of the moving object increases, the Lorentz vector gets bigger and bigger. And in fact, as the velocity approaches the speed of light, gamma approaches infinity. So it's clear that dt and dt prime can become drastically different. And therefore, when we say the force is the rate of change in momentum with respect to time, it really matters what time we're talking about. And as the object is moving relativistically, so at speeds comparable to the speed of light, we can't even approximate dt to be dt prime. Dt and dt prime are very significantly different. So it's very important we distinguish between dt and dt prime. So when we say force is the rate of change in momentum with respect to time, what time are we talking about? Time according to us, or time as we see it seem to pass for the moving object? Well, the force the object is being given is causing it to gain kinetic energy, but it will respond to the force based on how much energy the moving object feels it has gained. So in other words, based on things related to the amount of time that has seemingly passed for the moving object. So when we're saying force is the rate of change of momentum with respect to time, we mean force is the rate of change of momentum with respect to time t prime. So force is dp by dt prime, not dp by dt. However, since we're the ones trying to work out what the kinetic energy of the moving object looks like, we're the ones observing the object moving and therefore discussing its kinetic energy, we really want to rewrite force in terms of variables relating to our reference frame. So things like how much time has passed from our perspective for us. And therefore we really want an equation of f in terms of dt, not dt prime, but you can rearrange dt equals gamma dt prime into dt prime is dt over gamma, and then if you substitute that in to your relativistic definition of force, you get force is equal to d by dt of gamma p. Now, we have to keep gamma inside the brackets because our object is accelerating. We're applying force and it's gaining kinetic energy. And as it's accelerating, velocity is changing, and since gamma is a function of velocity, gamma will also change. So gamma is a function of time by virtue of being a function of velocity, but that velocity changing because the object is accelerating. So we can't pull gamma out of these brackets. We have to keep it inside these brackets. And now we're going to write f a little more explicitly because we really want to bring in the idea of mass into our relativistic kind of equations. Because we're ultimately after an equation relating mass and energy. So we say f is equal to d by dt of gamma m naught v, where we just gone momentum p is just the mass of the object times velocity, as we did in the classical case. But in relativity, I've used m naught instead of m. It's worth saying m and m naught on this slide are the same thing. However, in relativity, we use m naught because the mass is actually here is actually the Rass mass. M naught is the Rass mass. And in Newtonian physics, because we assume time dilation is 0, in other words, dt is equal to dt prime, that implies gamma has to be 1. And therefore, gamma m naught is always going to be m naught. Meaning the only kind of mass we're worried about in Newtonian physics is m naught, the Rass mass, so we can use any symbol we like for that. But in relativity, gamma m naught, due to time dilation, isn't necessarily equal to m naught, so it's important to distinguish between gamma m naught and m naught. And gamma m naught has units of mass, because gamma has no units. And therefore gamma m naught is a kind of mass, and we call that the relativistic mass. And in relativity, confusingly, the relativistic mass has a symbol m. So in relativity, if you see m, think relativistic mass. In Newtonian physics, if you see m, think Rass mass. But in relativity, we use m naught as a symbol for Rass mass. But the Rass mass is a constant, and we can put it outside of this bracket, and then we can use the product rule to evaluate the relativistic force, which we'll come on to in a moment. But it's worth saying the advantage of having a relativistic mass where we define it to be gamma m naught is that way we can still go, well, the force is equal to dp by dt, where p is mass times velocity. It's just that mass is the relativistic mass. So that's the advantage here of defining the relativistic mass, although we will see it comes into play in a much more physical and not just in a nice neat way when we use the product rule to get kind of like expand out these brackets and then get an expression for the relativistic force that is easier to physically interpret, which we'll then put into our equation for kinetic energy to get a relativistic equation for kinetic energy, which will have a term which is not zero even when v is zero, hence leading to the idea of E equals mc squared. Or, as we should say really technically, E equals m naught c squared. So we defined force to be the rate of change with respect to time from our perspective of m naught to gamma v. And we said we could bring the m naught outside of this kind of derivative because m naught is a constant. And then we use the product rule to evaluate what d by dt of gamma v would be. And when you do that, you'll end up with this expression for the force. This is just using the product rule. Now the challenge with trying to Newton this up into something that is more physically easier to interpret, so in other words trying to get a single term, is that currently we've got two terms in our expression for the relativistic force. One term depends on the rate of change of velocity, the other one depends on the rate of change of our Lorentz factor gamma. So if we could combine the two terms, we really want both terms to refer either to dv by dt or d gamma by dt. Now, gamma is a complicated function of velocity, so it'd be quite hard to change dv by dt into something to do with d gamma by dt, but we can do the reverse a lot easier. We can go from d gamma by dt and get a term that has dv by dt in it. And we do that through the chain rule, because the chain rule tells us that d gamma by dt is just going to be d gamma by dv times dv by dt. And that way we can replace d gamma by dt with something that has dv by dt in it, and then factorize dv by dt out. But if we're going to use the chain rule, effectively we're going to need to know what d gamma by dv is, and for that we need to know what gamma is as a function of v. And gamma is this function of v. It's a slightly complicated function, and it's actually the complexity of this function, particularly there being a square root and a v squared on the bottom, which makes the integral we'll have to evaluate for the relativistic kinetic energy quite complicated, although requires a fair bit of imagination to solve, hence why the best integrals are often involved. But the devil with proving E equals mc squared is often this, this not too straightforward function of velocity, this kind of Lorentz factor gamma. But anyway, now we have the Lorentz factor gamma, and we have the product raw, you can, using the using the equation for the Lorentz vector, you can work out what d gamma by dv will be, and that way you'll be able to write d gamma by dt in terms of some, function of velocity times dv by dt. And if you substitute that into your relativistic force F, you'll end up with this equation. Now it's worth saying I haven't gone through all the nitty-gritty steps, one by one, and that's because this channel is kind of mainly about the physics, and I like to make my videos fairly interactive, so I don't always go through all the steps in detail, but I try to provide all the steps necessary to derive everything we're saying. I don't want you to take me on trust. So we have our equation for the relativistic force. Now, it's worth saying that this is, as easy to interpret a definition of relativistic force as we can get. Something very special about this relativistic force, which is very different to a Newtonian force. So the relativistic force depends upon gamma, as well as dv by dt. Now, it's not a surprise that the relativistic force would depend on dv by dt, because dv by dt is just the rate of change of velocity of our accelerating object. In other words, dv by dt is just acceleration. So it's not a surprise that f should depend on acceleration. What is the surprise is that f should depend also on gamma, and gamma is a function of velocity v. It's not a function of dv by dt. And that tells us that the relativistic force not only depends upon acceleration, but also on the velocity of the object that is moving. And in particular, gamma will increase as v increases. So what this tells us is that as an object accelerates, to keep the acceleration constant, we have to apply more and more force. It's almost like the object is actually getting heavier and heavier, which doesn't happen in the Newtonian case. So the idea of the object getting heavier and heavier, you might think has something to do with relativistic mass, and indeed it does. Because if we could try to understand what's really going on, why we would expect in some ways the relativistic force to depend on velocity v, and thus for the force we have to apply to increase even as the acceleration remains constant. Well, we can go back to the core idea of how we got to this expression for our force. We got to this expression, and particularly the presence of the Lorentz factor here, through the idea of time dilation. And time dilation tells us that time seems to be moving at a slower rate for the moving object. Well, therefore, as the object is getting faster and faster, it seems to us like the object's clock is running slower and slower, internal clock, and therefore it seems to be accepting the energy we're delivering at a slower and slower rate. And so, in other words, less and less of the energy we are actually trying to give it is it accepting within any period of time. And therefore it seems like the object is almost becoming harder and harder to move, because we're applying energy, but we have to apply more and more energy just to get the object to seemingly gain the same amount of energy it had before, because time is moving slower and slower for that object as it moves faster and faster. And so it almost is like the object is getting heavier and heavier, in so much as it's resisting more and more the force we're trying to apply to get it to accelerate. And so therefore the idea of relativistic mass is very much a legitimate way to think about mass if we're defining mass as inertial resistance to acceleration, or how hard it is to accelerate an object. And that's just an interesting feature with the relativistic equation for force, and it's this equation for force is something we'll come back to at the end of this video. But because the main purpose of this video is E equals mc squared, we're now going to plug our equation for relativistic force into a definition for kinetic energy to get an equation for the relativistic kinetic energy of a moving object. Well, if we use a definition of kinetic energy and we plug our relativistic force in, this is what we get for the relativistic kinetic energy. Now the challenge really here is evaluating this integral. And this integral actually naturally lends itself to Lebesgue integrals. However, we're not going to go down that route. We're going to use integration by substitution as promised at the start of this video. And so what I'm going to do is I'm going to now show how I've done it. It's worth saying there are many ways to actually probably evaluate this integral, and there are probably many different substitutions you could do. I'm just going to show what I've done, but if you'd like to pause this video and have a go at evaluating this expression yourself, then you know, that might be a way to make this video fairly interactive if you would like to do that. I'm saying that because I'm about to spoil the potential fun of having an adventure with evaluating this integral yourself if you like doing integrals, because I'm about to ruin the joy of discovery by showing how I've done it. So now fair warning has been given. Let's get going with evaluating this integral. Well, whereas before in the Newtonian case I didn't put limits because I could, with common sense, argue about the value of the constants of integration, in the case of relativity we can't really use common sense, so I don't want to start to have constants of integration and then try to use common sense to argue about its value. Therefore, so I don't worry about constants of integration, I put limits in the integral explicitly and not putting a lower limit. The lower limit is 0, because we're talking about the kinetic energy in object gains from when it's initially stationary, so the initial velocity has to be 0, and then the kinetic energy of an object is equal to the energy it's gained between moving at a velocity of 0 and getting to a velocity of v. So the upper limit of our integral needs to be v. And now we have to evaluate this integral. Well, as I say, there's probably many substitutions you could do, but the first substitution I did was to deal in some way with both the fact that we're integrating two terms, gamma cube v, and also the fact that gamma is a function of v squared, whereas we're integrating over v, not v squared. And so to get around those problems, which aren't inherently problems, but they do make evaluating the integral quite complicated if we're going to do it directly, I got rid of the v squared by just going, well, let's replace v squared with u, so gamma is a function of u, and we're then going to integrate over u. So in other words, gamma just depends on u, we're integrating over u, so that's an indication that this integral might become easier to solve. But the other advantage with having v squared equals u is when we do substitution, it will turn out that we're actually just going to be integrating gamma cubed in terms of u with respect to u, because when we're replacing dv by du, the v next to the gamma cubed will get cancelled out. And it's because if we've got v squared equals u, then dv is going to have to equal du over 2v. So if we replace dv with du over 2v in our integral for the kinetic energy, then the v in the divided by 2v is going to cancel with the v that is multiplying the gamma cubed, and that way we are just going to end up integrating gamma cubed in terms of u with respect to u. So it simplifies the integrand itself as well. And so then you end up with this expression after the substitution. As you can see, we're just kind of integrating essentially gamma cubed. But the challenge really with now evaluating this is, well, I know how to integrate a variable to really any power in terms of that variable. But here we're trying to evaluate c squared minus a variable all to a power in terms of that variable. So one way I can get around that is just to go, well, that makes c squared minus u a new variable, and that's integrate in terms of that new variable. That way we'll integrate a variable to some power in terms of that variable, which we can work out using, very standard rules immediately of integration. And so if we replace c squared minus u with a new variable, which I'll call a, then we can work out the kinetic energy very simply. The also good thing about having a replacement of c squared minus u in terms of a is a linear in u, that way dA and du are directly proportional, so we don't get any of the funny business we often do when exchanging, the thing we're integrating with respect to in substitutions. And when you evaluate the integral in terms of u, and when you're careful with limits, it's worth saying, you'll end up with this expression for the kinetic energy. And I encourage you to, if you'd like to go through this in detail yourself, if you'd like to evaluate these integrals and convince yourself that this works. But because this is mainly physics orientated, we kind of try as much as possible, at least, to stick to the physics, but show the important steps and important ideas at play in the maths. So we have an expression for kinetic energy. A thing to note is that if we expand out the brackets, we're going to have the kinetic energy is equal to gamma m naught c squared minus m naught c squared. In other words, we're going to have a term m naught c squared, and m naught c squared is not a function of velocity. It doesn't depend on velocity at all, and it's non-zero when v is 0, and it's that bit of our expression for kinetic energy that turns out to relate to energy to do with mass, so m naught, which we'll look at in the very next bit of this video. So we're now going to evaluate our expression for kinetic energy in more detail. We've got as neat expression as we can for it, so if we just wanted a formula for the kinetic energy, we could stop there. But we want really to get to energy associated with mass, so we want to plough a bit deeper into this formula. Well, our formula for relativistic kinetic energy is here. Same one as on the we've looked at just now in the video. And because we want to look at mass energy, it's now worth actually expanding the bracket. And when we do it, we end up with this expression. And we can rearrange this expression. And when we do it, we have gamma m naught c squared is equal to relativistic kinetic energy plus m naught c squared. Now, in an equation in physics, if something, so let's say if A is equal to B plus C, then whatever units B has, C and A must also have those units. Because, for example, we can go, well, if we have 5 apples, like 5 apples and we had 2 apples, we end up with 7 apples. But if we had like 5 apples plus 2 bananas, we can only ever say, well, that's equal to 5 apples plus 2 bananas. We can't ever say that's equal to just a single term. Because bananas and apples are different. And because, units in physics tell you physically what a thing is, using a similar kind of line of logic, whatever the units of kinetic energy are, the unit, both m naught c squared and gamma m naught c squared have to also have those same units. Otherwise, we wouldn't be able to compactify kinetic energy add m naught c squared into a single term. Just as you can't compactify 5 bananas plus 2 apples into anything else, any one term, you have to just treat it as 5 apples plus 2 bananas, if I stuff it in the right order. Well, I mean, at least one can tell that this video is scripted. But this is our equation for some kind of energy, which is equal to kinetic energy plus m naught c squared. Well, this immediately means that m naught c squared has to have units of energy. In other words, there is energy associated with the mass of an object. Now, we're saying m naught c squared didn't appear in our Newtonian notion of energy. There was no need for it. But clearly in relativity, it's present. So, in other words, we have the total energy, gamma m naught c squared, is equal to kinetic energy plus the energy associated with Ra's mass. And we'll actually derive using 4 vectors in a little bit another way to get to gamma m naught c squared, which is more direct than kinetic energy, rather than using notions of kinetic energy. But the good thing of doing it through kinetic energy is that we also get freely, as a side, but that's really the main part of our video at least, that there is energy associated with Ra's mass. Now you might wonder, what does it mean to say that an object with Ra's mass has some kind of energy, or there's energy associated with Ra's mass? And it's an important question because often, it's just said, well, Ra's mass can be turned into energy. Objects can lose mass and convert that into energy. Or the reverse is true. Objects with Ra's mass can produce objects with no Ra's mass but energy. Like, for example, in annihilation, if you collide an electron with a positron, you'll produce a photon. A photon doesn't have any mass. So what has happened is the mass of the electron and the positron has been converted into energy, and that's the energy the photon carries. But has no mass. The photon has no mass because all of the original Ra's mass of the electron and positron has been converted into energy. But despite this, it's not very clear what it really means, because when we think of energy, we tend to think of things moving. So what does it mean to say, well, an object when completely stationary has energy, and to relate that with Ra's mass? Well, the key thing is, energy can be converted from one type to another. So providing any quantity has units of energy, and it can be converted into other types of energy that we more readily identify as energy, then naturally that thing has to be energy, in as much right as any other familiar form of energy. And because m naught c squared has units of energy, and as we can see through things like pair production, which is the opposite of annihilation processes. So when an object with energy but no mass, like a photon, is converted into particles with mass, we can see from observations like that that clearly more common types of energy, like energy associated with photons, and photons mean, so in a sense that's energy to do with motion, can be converted into this energy associated with mass. But also, we see in processes like nuclear fusion, the energy associated with mass is often converted into thermal energy, therefore allowing atoms and molecules or ions or whatever it is to move more rapidly. And so clearly mass energy can be converted into kinetic energy. And therefore mass energy for these reasons is a legitimate form of energy. So we mean that an object with mass has energy associated with its mass in so much as that it can lose some of its mass, and the energy can be converted readily into other types of energy that we're more familiar with, such as thermal energy. But we're going to now explore a bit deeper in terms of relativity, and particularly using the idea of invariant quantities, what mass is and why mass should be associated with energy. So having considered a fairly physical justification for thinking of energy as something with units of energy and that can be transferred into more familiar types of energy, we're now going to explain why there is energy associated with mass, but from a much more deep relativistic perspective. Now, relativity is ultimately about four vectors at its heart. We need four vectors to talk about invariant quantities, like mass, but also things like space-time intervals between events in space-time. And we also need four vectors to talk about how quantities can vary between observers that are moving relative to each other. So, for example, when we're looking at time dilation, we had to make use of the idea of four position, in particular, four vector, and the idea of its components in one reference frame, and then getting to components in the other reference frame using the Lorentz transformation matrix. So we've talked a lot about four vectors, and it's not a surprise then really that to get to the heart of a more mathematically or deep explanation of why there is energy associated with mass, we have to use special relativity. So, and by special relativity I really mean have to use four vectors to really get to the heart of this. So, M0, as we said, is a invariant quantity. Now, that's slightly a matter of technicality, to be honest. In and of itself, there's no real physics to the statement that the mass is invariant, or at least not much, because we define the mass of an object to be the mass you would measure for the object if it wasn't moving relative to you. And relativity tells us, special relativity, that there can only be a disagreement about something, be it, the time interval between events in a particular region of space, or the mass of an object, if only disagreement between two observers about this, if those two observers are, at least one of them is moving relative to that thing. However, we define mass to be the mass you would measure for an object if you are not moving relative to it. And since Ras mass almost demands no relative motion to the object, then of course all observers in special relativity are going to agree on the value of Ras mass. Because the only way disagreement could be caused due to special relativity is if one was allowed to, have a different velocity to the object and then measure the mass of that object. But that's not allowed because we define Ras mass to be the mass you measure for it when the object is not moving relative to you. And so because of that, Ras mass almost has to be a conserved quantity. Well, it has to be an invariant quantity, I should say. That is, all observers in special relativity have to agree on the Ras mass of an object. However, the real physics comes in when we go, well, what is an invariant quantity in special relativity? Well, in an abstract sense, an invariant quantity is a quantity associated with the length of a 4 vector. And that's because, when talking about how variables can change in special relativity, we're talking about viewing the components of a 4 vector differently by rotation of one's space-time axes, but you're not actually changing the vector itself. You're most definitely not squishing or squeezing the vector. So no matter what components you measure for the vector itself remains the same and it has the same length, therefore. So the way we think about space-time visually, 4 vectors in space-time, means that naturally the length of a 4 vector is going to correspond to some invariant quantity. And so if Ras mass is an invariant quantity, there must be a 4 vector associated with it, that the Ras mass, or at least some equation involving the Ras mass, is some kind of a length of. If we're saying every 4 vector has a, associated invariant quantity, we can flip that and go, an invariant quantity in special relativity must have an associated 4 vector. Now, the invariant quantity of the space-time interval has associated with it the 4 vector called 4 position. But we can take 4 position and we can differentiate it with respect to time to get 4 velocity. And then from 4 velocity, we can easily get 4 momentum. So based on how we've defined 4 position, as we will see in a couple of videos' time, we know what 4 momentum would have to look like. And it will turn out that m0c squared is actually the length of 4 momentum. Or if we're using kind of like natural units where we're just saying c equals 1 and has no dimension, then the length of 4 momentum is just literally equal to the Ras mass of an object m0. But there's a curious thing about the units of the invariant quantity and the units of the components of the 4 vector the invariant quantity is associated with. And we can exploit that to understand why there has to be energy associated with the Ras mass. Now, it turns out because we define the length of a vector using a scalar product, that the length of a vector has to have the same units as the components of the vector. And this is true, providing we're using the scalar product to determine the length of a vector. or particularly we're saying the length of a vector is we define to be the scalar product, well, the square root of the scalar product of the vector with respect to itself. It doesn't matter whether we're talking about Euclidean geometry, space-time, even general relativity. Well, actually, no, there's a subtlety with general relativity. So, actually, it's true in special relativity and Euclidean space. General relativity is a bit more complex. And if you want kind of like mathematical justification, one aims to look at the equation for the scalar product. So if we take x to be a 4 vector and our components, our contravariant components of our 4 vector are x mu, and the scalar product of the vector with respect to itself is by definition equal to the metric tensor of the space multiplied by x mu, x nu. So essentially, if you like, products of the components of our 4 vector. And the length we define to be the square root of the scalar product of a vector with respect to itself. So if we define the length to be q, then we just can say by definition that q squared has to equal the scalar product of the vector with respect to itself. Now in special relativity and in Euclidean geometry, the metric tensor doesn't have any units, because if you look at the metric tensor, all of the components of the metric tensor is just numbers. There's no units associated with them. And what that means is q squared has to have the units of x mu times the units of x nu. We don't have to worry about our metric tensor when looking at the units of q squared, because our metric tensor g doesn't have any units. And if the units of q squared is the units of a component of our 4 vector times the units of the component of our 4 vector, then the units of q would have to be just the units of our 4 vector. So in special relativity, whatever units the components of our 4 vector have, the invariant quantity associated with that 4 vector will have the same units. And as I say, the components that form momentum have units of energy, and therefore the length, which is m0c squared if we're using standard units, also has to have units of energy. In other words, there has to be energy associated with mass. So that's a more abstract mathematical way to look at it. Don't worry if that didn't make a huge amount of sense. It's worth saying that it's designed to be mathematically specific for those who would like a more technical explanation, but really the reason we consider energy to be associated with mass is because we can define legitimately and not just pluck it out of thin air, a term which has units of energy, which is important, which is about energy associated with mass, which doesn't have velocity in it. And also this energy can be converted into more traditional types of energy, so for all intents and purposes it is a form of energy. So now we've argued, both physically and more mathematically, technically, why there has to be energy associated with mass. We're now going to look at using for momentum to derive an equation for the total energy of a particle in relativity. So we've seen before we can get to E equals gamma m0c squared as the total relativistic kinetic energy when we rearranged our equation for kinetic energy. However, since a total relativistic energy is quite useful, particularly if something is moving so fast that the kinetic energy is actually comparable to the mass, so you need to take account of both mass and kinetic energy. It's worth having a more natural way to get to the total energy of a relativistic particle, rather than having to go through the kinetic energy route. And also in that derivation, we'll see yet another indication that there should be some kind of energy, at least part of the total relativistic energy, which should depend upon mass. So we justified essentially why mass is linked to energy, physically, mathematically, technically, but now we're going to see a similar, justification in a way, along similar lines. But it's going to be part of a way to get to E equals gamma m naught c squared through the idea of form momentum. A form vector we will properly look at in a couple of videos' time on this playlist. So, form momentum naturally is linked to the total energy of a relativistic object because momentum is obviously a very important part of energy. Momentum naturally relates to kinetic energy in the classical case. Momentum is also a part of the relativistic kinetic energy in a relativistic case. However, it's a bit more subtle, as we saw our equation for relativistic kinetic energy, than classical kinetic energy. However, relativistic kinetic energy still depends on momentum. So there's a natural link between momentum and energy. And so if we could derive an equation for the total energy of a relativistic object, we need an equation for the momentum of the object through three-dimensional space in the context of relativity. Well, we saw before when we were deriving, trying to get to an equation for the relativistic kinetic energy, that due to time dilation, the force we have to apply on the moving object is actually the time derivative of gamma m naught v instead of the time derivative of just m naught v. And if you want to define force as the rate of change of momentum, you can still do this with this equation. It's just your definition of momentum needs to be gamma m naught v in the relativistic case. And so this bottom equation here defines what's called the relativistic momentum. It's essentially a version of momentum that still allows us to say, even in the context of special relativity, that force is the rate of change of momentum. And so when I talk about relativistic momentum across three-dimensional space, I'm talking about P, where P is gamma m naught v, at least in this playlist on special relativity. Now, the way that momentum is linked to energy is through essentially a scalar product equation. So, as we'll see in a couple of videos' time, when we derive an equation for momentum, when you take the scalar product of form momentum with itself, that ends up reducing to this equation. And this equation looks like the scalar product of a four vector because it's got a component possibly of a four vector, and we will see it indeed is a component of a four vector squared minus another component of a four vector squared. So it has the form one would expect of scalar product equations and special relativity. That minus sign is there because space-time has a hyperbolic geometry. If you're talking about scalar products of vectors, in terms of finding scalar products of vectors, in A-level and stuff, when you're working with Euclidean geometry, there are no minus signs. You just add the squares of the components of the vector. But because of the hyperbolic geometry, we have a minus sign. Now, if you're not too sure what hyperbolic geometry is, say you're starting the playlist from this video, don't worry too much. I've got a couple of videos before this that go into a fair bit of detail on hyperbolic geometry and trying to visualize exactly what that looks like. But for our purposes, we can just take this equation as true, at least for this video. As I say, we'll come back to this in a couple of videos' time. But E here is the total relativistic energy, which is the thing we're trying to find. P is our relativistic momentum, through space anyway, so it's gamma m naught v. And m naught is our Erasmus of the object, whose relativistic energy we try to find. Now, an interesting thing about the scalar product equation is actually that it implies that there should be energy that isn't associated with momentum. Because if we could define Erasmus to be positive, which we essentially always do. In fact, if we define Erasmus to be a real number, so in other words, providing we're not talking about tachyons, then m naught squared is going to be positive. And therefore, if we're looking at the total relativistic energy of an object, which clearly has non-zero mass, then since m naught squared is going to be positive and bigger than 0, then E is going to have to be bigger than PC. Essentially, the total relativistic energy is going to have to be greater than an energy associated with the momentum of the moving object. And in that sense, there must be energy associated with the object, which has nothing to do with it moving, and that's energy to do with Erasmus. So that's another way that kind of the idea that there should be energy associated with Erasmus comes into the picture. So if we plug in our formula for momentum P into our top equation in the big blue box, we end up with this, and then you do a bit of algebra, using the equation we have for our Lorentz factor gamma, and you can reduce it to this, and then you do a bit more mathematical wizardry, and you end up with a Wörter equation, which is the total relativistic energy of a particle. Now it's worth saying, in my videos I tend not to go through the algebra step by step, because these videos are mainly about the physics, and going through the algebra doesn't really help in that regard, and it might distract from kind of like the core physics, and which I think is kind of core. At least E equals mc squared is I don't mean to be biased, so mathematicians please forgive me, but slightly more exciting than rearranging these kinds of equations. Not that rearranging isn't useful. I mean, as we saw with relativistic kinetic energy, rearranging that equation was very useful indeed. But a lot of the time in my videos I'll just leave out the full rearranging things, but hopefully I provide enough steps where if you'd like to follow along with this video, you can pause it at any time and then do the rearranging yourself, and that way these videos are more interactive, and it gives you a bit of stuff to play around with. And so now we've really said everything we need to about relativistic energy, so the total energy of a relativistic particle, and also the idea of there being energy associated with mass. We're now going to look at something I mentioned before and said I will come back to, which is the fact that the force on a relativistic particle depends not only on the acceleration of the particle, but the velocity of the particle itself. And so I'll just mention that. And in the last bit of the video, and then we'll just finish up. So I'm just going to briefly, as I said, go back to the strange feature of force for a relativistic particle. So in Newtonian physics, force is equal to mass times acceleration. In other words, force is equal to m0 times dv by dt. And the nice thing about this is this equation is kind of like, well, it depends on the force. But this equation at least allows, possibly depending on the force, for a linear equation which can easily be solved. A linear differential equation in terms of position x of your object which is moving, allowing you to quickly find the equation of motion for it. An example really is a simple harmonic oscillator where the force is directly proportional to the displacement of the oscillating object from its equilibrium position. So in other words, force is a function of position x and is linear in that. And because dv by dt is just the second order differential of x with respect to time, we end up with a linear differential equation, making it very easy to find the equation of motion. However, in special relativity, force, is always a function of not only acceleration but velocity too. And so whatever equation of motion you have, say for x, you're going to have on one side of an equation you have a force in terms of x, and then you can set that equal to this confusing thing, m0 gamma cubed times dv by dt, but because you've got gamma cubed multiplied by dv by dt, there's no way that that's going to turn into a linear differential equation in terms of x. And because of that, in special relativity, the equation of motion, so if we wanted to, write a differential equation for x, such that we could solve it to find x of t, is non-linear. And that makes finding equations of motions of relativistic particles actually quite complicated, which is why when you're doing particle, physics and stuff, even if one is going to ignore quantum mechanics, which adds even more complexities, but even if we could ignore quantum mechanics, one would never really want to use equations of motions, that is differential equations in terms of x that one can solve to find x as a function of time, because these differential equations would be non-linear. And to show how the force can vary kind of visually, I've plotted a graph where I've got our beta factors, so the velocity of a particle divided by c, and I've plotted how the force can change as we increase this beta factor, but for particles with different accelerations. And you can see that, no matter what acceleration we have, if we change the velocity of the particle, the relativistic force increases. Whereas in Newtonian physics, it doesn't matter what the velocity of the particle is, the the Newtonian force would, just depend on acceleration, and it would have nothing to do with the velocity of the particle. So we would just have a horizontal line, because the force wouldn't vary with our beta factor, or in other words, v/c. So this idea of Newton's essentially, it's why you'll never really see an equation of motion, special relativity, or at least want to use one generally to understand the dynamics of a relativistic system. And it turns out that general relativity is also nonlinear, but in a much more complicated way, which is why finding equations of motions in general relativity is incredibly tricky, and I think it's still the case that a two-body problem, so when you're looking at how two masses move, due to the gravitational influence of those two masses, that simple problem, at least simple in terms of classical gravity, hasn't been solved exactly in the context of general relativity. We've got excellent, very good approximate solutions, but I don't think we yet have an exact solution, because even that simple problem, the nonlinear nature of forces and relativity makes that very difficult. So when you're talking about things like black hole collisions, loads of approximations and clever stuff goes into trying to understand what's happening there, because we can't solve it exactly with general relativity, at least not in the general case. So, a bit of a detour to general relativity, but it's worth seeing, how the things we're doing here can sprinkle into other realms, such as, general relativity. Particularly, there might be a playlist on general relativity at some point, so, it's good to bring in other things into this topic. Now the next video we're going to look at the next video we're going to look at seeing why we need equals mc squared to understand how the sun can produce such vast amounts of energy, and then after that we're going to look at form momentum in some detail. But this is everything for this video, so we covered a lot. We derived E equals mc squared, or more properly, E equals m naught c squared, as long as the particle has no relativistic momentum, at least through space. But we've also understood why that's true, why we should associate energy with mass, and link that into some technical ideas about scalar products, but also talked about it more physically, in terms of transfer of energy and that kind of thing. So that's everything for this video. I hope this video has been helpful, hopefully approachable. Let me know in the comments if there's anything you want me to improve upon, and look forward to seeing you in the next video, hopefully, where we'll talk in fair detail about our wonderful